Hi everyone, and welcome to another measurement and instrumentation class. In the previous class, we finished the introduction on measurements and different parts of the measurement instrumentation systems, such as transducers, amplifiers, analog to digital converters, and also we spoke about what mean and standard deviation is and where do we use them. We also solved the problem on calculating the mean and standard deviation. I will post this first set of homeworks this week. You're going to have 10 days. It's going to be about calculating the standard deviation and the average in the measurement system. Now, today we will continue with error, different types of errors. We will solve some practice problems on absolute errors and relative errors and different types of errors. If we have time, we would speak about precision and accuracy. What do they mean? And we will solve some practice problems on accuracy as well. Before I start, do you have any questions from the previous week? No? Okay. So let's start with errors and different types of errors. We have three main types of errors. We have the absolute error, we have the relative error, and the percentage error. These are three ways that we define errors here in this class. Now, for calculating the absolute error is the difference between the measured value, and we had this in the previous class as well, and the true value. And this is the equation. Again, absolute error is going to be the true value minus the approximate value, or the measured value. Now, as you may recall from the previous class, the true value means the value that we know that it's 100% accurate. How do we measure that true value? By measuring hundreds of times, for example, or tens of times, and getting an average for that. So, for example, if you're measuring the room temperature, you can measure it 50 times in a minute, and that would be and get the average of you can calculate the average for that, and that would be your true value. And if you subtract that from the measured value at that time, then you get the absolute error. Now, for example, assume that the analysis of an iron ore by some method gave 11.1%, while the true value was 12.1%. We want to find the absolute error. So again, the absolute error is going to be the true value, which is 11.1, and the measured value, which is 12.1, which gives us around 1%. Now, to measure absolute error, as mentioned, true value minus the approximate value gives us absolute error. But to find the relative error, it's defined as the absolute error divided by the true value. So again, relative error is the absolute error divided by the true value. In other words, it's going to be x minus x prime over x. So for the same problem, previous problem, the true value was 12.1 and the absolute error was 1. So the relative error is going to be 1 divided by 12.1 times 100 gives us a relative error of negative 8.3%. Usually we just are interested in the magnitude, which is going to be equal to 8.3%. So most of the time we show the error using the relative error. And for measurement tools like a DMM digital multimeter, you would see this usually in the manual or the data sheets of the DMM, which shows the relative error. So for example, if it shows a relative error of 5% in for measuring voltage, means that you have a 5% error in the system. And that 5% is usually the maximum error that you get. Another type of parameter that we use is called the relative accuracy. This is the percentage of the quotient of absorbed result to the true value. So for the previous example, the absorbed value or the measured value was 11.1, and the true value was 12.1. So the relative accuracy is 11.1 divided by 12.1 times 100%, gives us an accuracy of 91.7%. Let's solve another one. We want to find the relative accuracy. The measured using a multimeter, we have find the current, the measured current, I'm going to call that, or absorbed current, I'm going to call it IM, is going to be equal to 5.67 amps. And the true value, I'm going to call it IT, is going to be equal to 5.7 amps. I want you to find the relative accuracy. Okay, so relative accuracy would be equal to the observed value or measured value, which is 5.67 divided by 5.7 times 100. What is it? What did you get? I'm sorry? 99.5%, which is a very high accuracy for measuring for a consumer-based measurement tool. Now, the percentages of error, sometimes we need to find the percentage of error. It's going to be EP, or percentage of error, is going to be 100 times ER, which is the error that we had. The relative error. So for the previous question, again, the percentage of error for here was going to be that 8.3%. But let's solve another example for this. Suppose 1.41414 is used as an approximate to square root of 2. Find the absolute, relative, and percentage error. So square root of 2, the true value is 1.4142136. So the absolute error is going to be equal to the true value minus the approximate value, which gives us 0.000021356. Now, if you want to find the relative error, again, this is the absolute error, or EA. Just subtracting the true value from the approximate error value, the approximate value. And now, if we want to find the relative error, it's going to be the error that we found divided by the true value gives us 0.151 times 10 to the power of -3. So this is a relative error. And if we want to find the percentage error, we just simply multiply this by 100 to find the percentage. So multiplying that by 100 gives us a percentage error of 0.151 times 10 to the power of -1. In other words, it's 0.01%, which is very low. What if we want to find, I want you to also find relative accuracy. So relative accuracy in the system. Again, the true value was the true value was 1.41421356, and the measured value was 1.414. And this would be time. It's going to be 99.99 something percent. Let me calculate it. It's 99.98%. Going to be 99.984%. And this is the relative accuracy. I'm going to show it with R. Now, another example. Imagine we want to measure something's length, and the length is 122 millimeters, and the true value is 122 millimeters, and the measured value or expected value or observed value is 120 millimeters. If we want to find the absolute error, it's going to be 122 minus 120 gives us 2 millimeters. The relative error is going to be the error divided by the measurement, which just gives us the true value, which is gives us 0.017. There is a small error over there. And the percentage of error is going to be 0.017 times 100, gives us 1.7%. This should be divided by the true value, and the true value is 1. But the result is the same. It's 0.017. Okay. Now, classification of errors. These are the general classifications for errors. For consumer products or purposes, 5 to 10% error is acceptable. For engineering purposes, 1% error is acceptable. And for scientific, anything above 0.1% is not acceptable, so it must be below 0.1% error. One example for consumer purposes is going to be the digital multimeter, also resistors that you buy. I think most of you are already familiar with the resistors. They are color-coded, and they have either a gold or a silver ring at the end, because that gives you the amount of error that you are expecting, or tolerance that you're expecting. It's 5 to 10%. But if you want to build a transistor, have a transistor for very high, engineering project, you need higher quality resistors, for example, that have lower errors. Now, Another term that we have is called the range of uncertainty. It's reported as a nominal value plus or minus an amount called the tolerance. So if the reported value is 120 millimeters, and the tolerance could be plus or minus 1 millimeter. So it's between 119 and 121. And you're going to see this, you already had this in Electronics 1. When I was teaching that class, I usually taught that as well. Imagine you have a resistor that it's 1,000 ohms, and the tolerance is 5%. Okay. What is that? What is the range of that uncertainty for this resistor?
950.
Thank you.
1050.
Yes, it's between 950 to 1050 ohms. So anything between this, if you measure it, you're going to see it's probably like 980 or 1020, something in that range. If it's above that, then it's not going to be 5%. Tolerance is going to be more than 10%. And you're going to see it on all, consumer products as well, from milk to anything. You're going to see it says this is like 1 gallon plus or negative, minus, 100 cc or 5 ounces or something like that. Now, the range of uncertainty could also be measured in percentage as well, as I mentioned. So instead of adding a certain number, you can add percentage. For example, you can say that the range of uncertainty is, for this one, the nominal value is 120 millimeters plus or negative 2%, which is our tolerance. So again, this one is going to be between 117.6 to 122.4, because 2% of 120 is 2.4. Therefore, it's going to be 120 minus 2.4 and 120 plus 2.4, which we saw in the previous example for the resistor as well. Now, some performance characteristics of measurement systems. One of the most important one is accuracy. It's the degree of exactness or closeness of measurement compared to the expected or desired value. We have a resolution, which is the smallest change in a measurement variable to which an instrument will respond. We have precision, a measure of consistency or repeatability of measurement. Then we have sensitivity, the ratio of change in the output response of instrument to a change of input or measured variable. We have the expected value, which is the design value or the most probable value that we expect to obtain. And finally, we have error, which is the deviation of the true value from the desired value. Now, what is the difference between accuracy and precision? Imagine you are in a shooting range and you have a target. Okay. What is the difference between being accurate shooting at this and being precise? Yes, hitting around this is going to be. What about precision? On the expected target. So if I hit this like this, am I accurate or precise? Who says I'm precise? Okay. So scenario A, I have 6 shots and I shoot them like this. Scenario B, I have 6 shots and I do it like this. And this is my target. The red one is my main target. Scenario C, I have 6 targets, but it's like this. And finally, scenario D, I don't have a different color. I would do it with red one. So scenario D is the red one. I have 6 shots, but it's like this. So scenario A, am I precise or accurate? Am I precise? Who says I'm precise on scenario A? I shoot everything is clustered, it's close, but not close to the target. Precise. Who says I'm accurate? Okay. So the rest of you don't have any opinion. So, okay. So scenario B, am I precise? Am I accurate? Yes. So B is accurate and precise. What about C? I'm scattered all around. Am I precise? Am I accurate? No. What about scenario D? Am I accurate? Am I precise? Okay, that's correct. Yes. So measurement of precision must be interpreted in light of measurement of accuracy. Let's use as the target practice example. In the best situation, again, the shots are tightly clustered, high precision on the center circle, which is highly accurate as well. Scenario B, this is accurate because it's around the target, but it's not precise. It's not clustered enough, okay? So you can see it's scattered more than the first one. If you go back, you can see that the first one, almost all of them is in the yellow circle. The second one, a lot of it is out of the yellow circle. So it's accurate, but it's not precise. And you can read faster than I can. Now, this one, it's scenario A that we had here. We are precise because everything is clustered, but we are not accurate because we are far from the target. Okay, so this is precise and not accurate. And the final, the worst case scenario, we have no precision, no accuracy. It's scattered, it could be all around, and it's far from the target. So again, putting all together, best scenario, we're accurate and precise. Worst scenario, we're not accurate or precise. And the third one is going to be we are precise but not accurate. Now, obviously, we want the best scenario, but being precise but not accurate is also very good as well. Because with a little bit of shifting or putting a little bit of bias, we can move that towards our target. That's the reason, I don't know if you've been in target, how many of you have been to a shooting range or, okay, you're almost familiar, it's Texas, all you see everyone is a gun. But when you go there, you would have like 3 shots. And when you shoot those 3 shots, for example, and you connect the middle, and if it's like 2 inches above the target, imagine the target is here. Okay, the blue one is the target. What you're going to do, you first aimed for the target, but everything was clustered here. Now what you want to do, you want to aim here to hit the target. Does it make sense? So you know that you're precise, the accuracy of the gun is good, but you're missing the target by 3 inches or something like that. And the same thing for measurement as well. You want to be accurate and precise, but if you're not accurate, but you're so precise, it's easy to correct that. One example that I can give you is measuring voltage. If your voltmeter has an error, what we call a drift of 2 volts, you can measure all your voltages and then finally add 2 volts to it or subtract 2 volts to it. Now, the worst case is going to be not being precise or accurate. This one is very difficult to correct sometimes. I would say accuracy is easier to correct than precision. Precision is sometimes very difficult. It could be, but you need a lot of measurements. You need to do like 1,000 measurements, and there are different algorithms. One algorithm, you can use machine learning algorithms such as KNN or SVM. KNN is the nearest neighborhood. You can just, like the same thing that I showed you with target practicing. What you do is you take an average of all of them and find the distance from each of these and find the geographical average for that, and that's going to be your average, and you can make it precise that way. Is it clear, or do you want me to? Now, let's solve an example. I want you to solve this. Given expected voltage value across a resistor is 80 volts, the measurement that we did is 79 volts. So the true value is 80 and the measured value is 79. One, we want to find the absolute error. Two, we want to find the percentage of error. Three, we want to find relative accuracy. And four, we want to find the percentage of accuracy. And I'll give you a few minutes. But actually, it's better to just give me a second to give you each a paper. That's going to be your, if you can divide that, because I don't have enough paper. So this is going to be your attendance and quiz for today. And please put your screens away. I'm sorry? Yes, yes, I'll give you the equations that you need, so you don't need to actually have that as well. Give you. Do you have a paper? Please write your name and your buff ID. Divided or I don't know. I don't know. Give you a password. Oh, you already have? Okay, good. I thought I don't have enough. So I'm going to go back to the equation. So if you want to write it down, the relative error is the error divided by the true value. You can write this down. The relative accuracy is going to be the observed value over the true value times 100% to make the percent. And then absolute error is the true value minus the measured value.
Go back to the example slide.
Yes, which one do you want me to?
Just what we're supposed to be answering.
Oh, yeah, sorry. Yes, sure. Yes, just give me a second. Why don't you go back to the relative accuracy?
Is this an electrical class or is it for all engineering?
No, this is for electrical. And when we go, further, you're going to see we're going to dive deeper into. It's just about sensors. You don't have a lot of that in mechanical engineering, but there are some concepts. I know at the beginning it may seem very easy, and it is. But it's a part of like your FE exam. You're going to have 5 questions on this as well. So it's it's easy thing to easy part of the FE exam to get as well. But yeah, well, we need to know the concepts before we start to dive deep into the measurements like the voltage, current, sensors, especially how you measure Whetstone bridge is a big part. You're going to have usually 1-2 questions on that as well. Did you all answer it? Do you need more time? No? Okay, give you 3 minutes to 1:40. And for your first exam, I didn't put a specific date on it because I didn't want to have conflict with your other classes, of course, exams. I was thinking the last week of February or the first week of March. We can have a vote, and if you're okay with the last week of February, we can do it on the last week. Like, do any of you have exams on there last week? No? Okay. So we can put it on the last Thursday of February. It's for now. Okay. Yes. So it's just the accuracy, the relative accuracy that we found. Yes, yeah.
So the relative accuracy, is that not the same as like the percent of accuracy?
That one doesn't have the percentage, the 100. You just have, if you find that, you're going to find both of them. So it's okay. Yeah. 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 The relative, and you multiply it by 100. Yeah. Yeah. There was a typo on the slide that multiplied by 100 as well. The maximum relative accuracy would be 1. So anything. Okay. If you're done, can I have the, thank you. Again, the main purpose is attendance. 50% is attendance here, and the other 50% would be the. Thank you. Can I have?
Yeah.
If you're done. Can I please
Yeah.
have?
Yes.
So the absolute error obviously is going to be the true value minus the measured value, which is going to be 1 volts. The percentage of that is going to be 1 divided by 80 times 100, gives you 1.25%. Relative accuracy, you just technically can divide, you can subtract that by 100% and you get almost this. So the relative accuracy is going to be 1 minus, or in other words, it's going to be the measured over the true value, gives us 0.9875, and the percentage of accuracy is going to be 98.75%. Now for again, this is very easy. You can just subtract 1 minus 0.125 and you get the relative accuracy as well. Now, next example, imagine we have multiple measurements and we want to find the precision of the sixth measurement. Now, to measure the precision, what we do first, we need to find the average of the measured values. So how many measured values do we have? We have 10. We're going to add all of them and divide it by 10. And that gives us our average measured value, which here for this particular example is going to be 1005 divided by 10 gives us 100.5. Now the sixth reading precision, we want to find the sixth reading, which is going to be 100. The sixth reading here was 100. And what we want to do is we want to subtract that from the average to see how far is that measured value from the average. And for this, it's going to be 100 minus 100.5 divided by the average, which is 100.5, and it gives us a precision of 0.995. So when you want to find the precision, again, you want to find the average. You don't care about the target. You don't care about the true value. You care about the average, because this may be far away from the true value. So here your true value may be 110. So the system is not accurate, but it's precise because everything is clustered around. So the more precise you're going to be, these numbers are going to be closer to your average. Therefore, you're going to have a higher precision like this one. Okay.
Why is the sixth reading selected?
This is just arbitrary. You can, this is for the example. I could say fourth, fifth, second, any of them. This is just for this example. But in the exam, I may ask for the third. That's a good question, by the way. Let's do it for the third. I want to find the precision for the third reading precision. So for the third reading precision, again, the average is the same, doesn't change. It's going to be 1 minus 102 minus 100.5 divided 100.5. So this is going to be equal to 1, I don't know where to write it, 1 minus 1.5 divided by 105, 100.5. Just give me a second. It's going to be lower than the previous one, but it's going to be 98.5 or 0.985. So you can see that closer that we are to average, we have a better precision in the system. That measurement, that measured value is more precise, I would say. Yeah. Is it clear, or do you want me to? Okay, so precision is about average, accuracy is about the true value. Okay. The precision, again, is the distance from the average of all those measurements, and accuracy is going to be the distance from the true value. Now, if the average is the same as the true value, then we have a very precise, very accurate system. So if in the exam I ask, well, in a accurate and precise measurement, what is the relation between the average values and the true value? They must be the same. Now, the accuracy of measuring instrument is guaranteed with a certain percentage of full scale reading. For example, manufacturer may specify the instrument to be accurate at plus negative 2% with the full scale deflection. For reading less than full scale, the limiting error increases. Now, an example of a limiting error, imagine we have a 600 voltmeter with an accuracy of plus negative 2% full scale. We want to calculate the limiting error when the instrument is used to measure a voltage of 250 volts. This was the exact problem that I gave for the previous semester. I didn't even change the numbers for the first exam. Now, the magnitude of limiting error is going to be 2%, which is 0.02 times 600 gives us 12. Now, therefore, the limiting error is going to be the percentage of that limiting error or over the scale, the voltage measurement, which is going to be the 12 over 250 times 100 gives us 4.8%. Let me give you another example. Imagine that we have an 800 volt voltmeter. The accuracy is 3%, positive, negative 3%. And we want to calculate limiting error when the measurement is used to measure a voltage of 300 volts. Again, 800 voltmeter, accuracy is for positive 3 or negative 3%. And we want to find the limiting error when the instrument is used to measure a voltage of 300 volts. Did you get the same results? Yes. Okay. So 3% of 800 volts gives us 24 volts. Now we would divide 24 volts, but the measured voltage that we want to do 3%, 300 volts. Therefore, the limiting error here is going to be 8% or 0.08. Okay. So again, if you have a galvanometer, a digital voltmeter, and it says the full scale error, not the error itself, full scale error is 1%, and the voltage is 1,000 volts is the full scale voltage, meaning it's 10 volts. And if you want to measure 100 volts with that 1,000 volt meter, you're going to have, instead of 1%, you're going to have 10% error now. So the voltage could be between 110 and 90 volts, which is a huge number. So full scale must be very, very small, full scale or limiting error. Now, if we have, this is another example, a galvanometer or a digital multimeter or a energy meter, a power meter, and it has a limiting error for example of 2% for its voltage, another 2% for its current. When we want to find the power, which is combining the voltage and current, because as you know, P is equal to VI. So this voltage has 2% and this is 2%. But when we want to find the power, we don't multiply it. We actually add those errors together. So the total error here is going to be error of, or the limiting error of the power is going to be equal to 2% plus 2%, which is 4%. This was an example. Now, an actual example that we have here, given for a certain measurement, a limiting error for voltmeter is, at 70 volts is 2.143%, and a limiting error for ammeter at 80 milliamps is 2.813%. We want to determine the limiting error of the power. So the limiting error for the power is going to be the limiting error of the voltage, which is 2.143, plus the current, which is 2.813, gives us 4.956%. So the voltage and the currents are just for distraction. It doesn't mean anything. The important part is just the limiting. So if you have a question like this on the exam, just the percentage of the errors are important for us for the current and the voltage.
So in the event that you were given percent error or say like power and the current, and you needed to find voltage,
You just subtract. Yes, perfect. Yes, that's a great point. Yes, you just subtract them. Power gives us a total error, the combination, yes. Now, we learned about different type of errors, limiting errors, accuracy, absolute error, relative error. And in summary, and we learned about other types of error. Human errors can be due to faulty techniques. For example, as I mentioned, wrong readings, such as like reading 21.5 instead of 25.1 that we saw in the previous lecture. Parallax errors can be avoided. Anomalous results can be seen on a graph. Then we have random errors that can be reduced by taking many readings and then calculating the average or the mean. And we learned about standard deviation and average and how we use that to determine an error. And then we have systematic errors, including zero errors, which will cause all your results to be wrong as well. And we were able to find and calculate errors as well. So some errors where you can mitigate, you can compensate. For example, if you don't have an accurate system, you have the precise system, you could just shift it, zero error drifts, or having random errors. But sometimes when you have a systematic error, it's very difficult to compensate that. But the best way always in errors is to do multiple measurements. That's the reason we usually don't rely on just one measurement. We do it multiple times at different times with different equipments. That's it for today's class. If you have any questions, I will be happy to answer. We already took the quiz. For the online students, I will post an online quiz. For now, your first exam would be at the end of February, the last Thursday. For the online students, it's going to be that weekend. If you have any questions in the meantime, just please email me, or you can come to my office at my office hours. Thank you so much, and I will see you on Thursday.
What is parallax?